All right, our last short talk will be by Tian from Microsoft, and will tell us about accelerating materials design with AI emulators.
Thank you very much for the introduction. And my name is Tian. So I'm from Microsoft Research AI for Science. So it's great that Wendy mentioned the work that we at Microsoft have been working from our close partner Azure Quantum team, working with PNL to really apply AI, right, to finding some battery materials. So today I'm going to talk about some work we have been doing at Microsoft Research AI for Science, right, ready to think very deeply what are some of the foundational capabilities we need to build around AI to accelerate material discovery. So just to, for those who are less familiar, just to give a brief interview about where we are. So we're part of Microsoft Research, and you might be wondering why Microsoft is working on like AI for Science now, right? We think Microsoft is like fully committed around the AI and its impact it's going to make around the world. And we do believe that science is one of the most important areas where AI can make around towards our society. So therefore, around 2 years ago, so Microsoft Research decided to build an institution specifically around AI for science. And we have been we're a global organization spanning across the world. I think 40% of people are in Europe and 40% of people in China, and maybe around 10% people are in the US, in Redmond. So obviously, I'm part of this team where we're trying to kind of push AI for materials because we think that AI is really, materials is one of the key areas where AI can make impact. But obviously for this audience, I don't need to explain, right, why materials design is important. Materials design is really the cornerstone of many problems to our society, right? So many of the really key challenges that we need to solve, say, for climate change in the next 30 years, is really bottlenecked by finding a good material, right? So if you find a material that can absorb carbon from atmosphere, it will be a key component of this. Many predict to be a very large industry of carbon capture, which will be key for us to achieve carbon zero in 2050. So yeah, the central question, right, in materials design is really about finding a material whose properties satisfy the design requirements for your application, right? So here is still a slide from Professor Xu Pingong, which illustrated some of the key design requirements for the solid-state electrolytes for the lithium batteries. So the key question, in the past decade, right? So this community has been building a lot of the tools or workflows, right, really to compute these properties and do large-scale computational screening to find the materials. But the key question here is that how can AI really accelerate this process, right? What are some of the key fundamental capabilities we need to build around AI, right, to accelerate the material design process? And this is the key question we're trying to solve, right, at our team. So in our view, there are two major key capabilities that we need to build around AI, right, to accelerate the discovery. The first part is what we call AI emulators, right? So using DFT, we can, or molecular dynamics, can already compute a lot of problems, but very often these are quite slow, right? However, because we can actually use DFT to generating lots of data, and at Microsoft, we have a huge amount of compute, so we can actually use this data to train a big machine learning model. So therefore, you can imagine that we can build up these AI emulators that can run at least the 3 to 5 orders of magnitude faster than DFT. And one of the typical such example is really this universal machine learning force field. And this is kind of why we are building this. So I'm going to talk. So the key kind of outcome that we have announced, we have building around the AI emulator is this model which we call MetaSim. It is a universal machine learning force field that's trained for structures across a periodic table. And so it's built on top of like MCGNet at the beginning, but we actually sampled a lot of configurations that have far away from equilibrium at high temperature pressure, because we think these are the regimes, right, that is very often undersampled in previous works. And we hope that by sampling these regimes, you kind of explore much bigger planetary surface. This allows you to unlock many new capabilities. So the two key innovations inside the medicine. The first is, as I said, really about the data. So we developed a active learning pipeline guided by the uncertainty from our networks, and really to iterate that with DFT to generating huge number of data. So it's like we generate around 17 million structures. So, and the key point here is that all these are very highly uncorrelated data because we use active learning uncertainty guided, meaning that we kind of decorrelate all the training data. We only compute DFT on structures with high uncertainty. So therefore, even though this is not such a huge data set, but it's actually very, very high quality. So the second part is really the model. So because we're trying to really fully utilize this data set, so therefore we move towards a transformer-based architecture, which is based on a model called Graphoma. It's also from MSR. And this is a much more scalable structure. We found that at the large data set limit, this actually performs much better than the previous MCGNet, which was the work, also the work with battery work that we collaborated PN with built on. So yeah, as a result of these innovations, this actually leads to broad improvements over many of the problems, like energy prediction, and also the prediction of phonons, and also the prediction of elastic tensor, etc. And in this very popular MapBench discovery data benchmark, which was also mentioned yesterday, we were actually at the top, but very recently this new model for the orbital AI that actually is a little bit better than us. So, but it's quite interesting that now this becoming quite a hard field that many people are really pushing, right, for moving forward this universal machine learning force field area. Another point I want to add is that actually it is trained at the PBE level of Siri, meaning there are some problems that you cannot tackle very well, right? One example is water, that you cannot really simulate water very well with PBE level Siri. So therefore, you can actually fine tune it to upgrade that to a high level Siri. So here we fine tune that using hybrid functional. You can observe a 30-fold data reduction if you fine tune that. So that's actually an advantage, right? If you have a base model that have a basic understanding about how this potential energy surface works. So that's kind of a key capability I mentioned, which is about AI emulators, right? So, I think we think this is the only part of the problem, right, in solving materials design, because let's assume you want to find a battery material, right? But then you screen 1 million candidates, but out of the 99.99% of the candidates, they will be bad, right? So they will not conduct a lithium at all, right? So therefore, you really need to have a more targeted way to search the chemical space, and this is where this AI generators come in, right? So by solving this inverse problem, by starting from the property that you're looking for, right, you can have a much more targeted search of the chemical space, and this would lead you to another 3 to 5 orders magnitude acceleration. And this is what we're building with our next model, which we call MetaGen. So MetaGen is, I think, the world's first model that generative model for inorganic material that truly demonstrating that you can do property guided generation over a broad range of properties, right, including magnetic, electronic, and also specific chemistry. And so there are a lot of a generative model before, but I think this is the first time we convincingly demonstrate that you can do this over a broad range of different properties. So at the heart, it is a diffusion model that was specifically built for materials. I will definitely not go into details for this talk, but there's a lot of specialities about the periodicity, etc., around materials that we need to tackle that are built into this diffusion model process. And also a very key important part for MetaGen is really about the data, which is the same for medicine. We actually created this data set that incorporates 600,000 structures, incorporating many open structures from Materials Project, ICSD, and also Alexandria data set, which is actually a very large exploration of unknown materials. And we combine all of them and we recompute DFT, and then we use to train our model. Actually, as you can see, compared with the previous baseline CDVAE, so there is a part, I think the model improvement give you around 1.5 improvement in performance, where the data gives you another 1.8. So therefore, the data is really, really important from our learning. So, but obviously the most important question is not really about generating a random material. The most important problem is about generating useful material, right? So therefore, we can actually fine tune this space model to accept any condition C, so that you can fine tune this space model to generating materials guided by any property of the material you're looking for. It can be a specific chemistry, or it can be symmetry like space group, or it can be any property that you can compute. Anything that you can label, you can generate label for these materials, you can use this to fine tune the model. So here's an example where we fine tune the model on chemistry and then use it to kind of explore novel materials. In this strontium vanadium chemical system, actually we benchmarked some of the baseline methods like random structure prediction or substitution. We actually found that the model is actually outperforms this model. I think, and also especially in like multi-element system, like 5-element system is really good because basically this is a much bigger space. So therefore there's an advantage of using generative model rather than starting from scratch. And one thing that is very significant here is also that we show that you can actually drive this generative distribution guided by broad range of properties, including magnetic density, band gap, and a bulk modulus. And a significant result here is that you can actually shift this data distribution, which is the purple blob, very far away from the training distribution, which is the green distribution, right? So it's quite surprising. For example, you can shift this to top 1 or top 0.1 percentile in the property distribution, because in many of the material design problems, you're really looking for finding, say, a super hard material, very strong magnets, or right, superconductors, etc. Right. So this ability to shift the property distribution is very significant. So this is the kind of a brief overview about some of the work we've been doing. And so we've been trying to kind of build up these foundational capabilities that allows you to explore novel materials, and also by working with our partners like Tian and Now, really to bring these capabilities into real world impact. So that is what we're trying to work on. So I just want to highlight that all this work is really, really kind of a highly collaborative teamwork here. At AI for Science, we have many FTEs and also interns who contributed to various part of the efforts, and also the medicine is driven mostly by our Euro team, and also medicine is mostly driven by Asia team, but work very, very closely across the organization. So thank you very much for listening, and I look forward to the panel discussion.